Okay, good evening, y'all. Hopefully you're all sitting someplace a whole lot cooler than Tech. Tech is a little bit warm on campus. I don't know if they have the air system down where it's supposed to be when it's this hot. My understanding is it's like the temperature factor outside is like 105 degrees right now. So hopefully things will cool down a little bit later. What we're going to talk about tonight is we're going to kind of deep dive into ANOVA. We'll start off discussing factorial ANOVA. Next week, I'm going to back off a little bit. We'll get back to discussing t-tests, one-way ANOVA, and also talking about ethics and research, and then maybe work in a little quasi-experimental research design considerations. In other words, for those of us that are applied psychologists, a lot of what we're going to be doing in workplace settings or other applied settings is going to be quasi-experimental research. And you know, from previous discussions, the idea is that we're applying the scientific method to something where we can't really control the assignment of participants to conditions, or we can't really control the environment. So, you know, the example I gave previously was if you look at somebody who really tries to control those things and does experimental research, that would be Dr. Walsick. Hadi, me, Sheets, the cells, what we usually end up doing, I should say just about 99% of the time, we end up doing quasi-experimental research if we're working in an applied setting. However, having said that, I think all of us at one time, you know, maybe 99% is a little bit too high. When we've done research on campus, a lot of times that has actually involved true experimental method. Well, I'm going to slide the computer over, show you some things on the board. Hopefully this shows up. Hopefully I've got a dark enough marker. With t-tests, you know, the bottom line, what we were looking at was if we had two means, and those two means are different, which is going to be anytime you go and sample two different populations, or anytime you measure the same people twice, there's going to be a little bit of fluctuation, correct? In other words, you know, I previously talked about how you could do that with your own weight. You could measure your weight on day 1 versus day 2. There's going to be some difference there. Same thing with height. You know, we're going to vary a little bit. And whether or not that difference was anything meaningful, you know, that's where you need to test it against probability. In other words, if my height fluctuates by half or 3/4 of an inch over the course of a week, probably what I'm going to see is I'm going to see kind of a continuing pattern where, let's say, okay, 3/4 inch range. And I'm slightly under 6'1", so let's say here's 6'1", and here's 6 foot. Okay, if I measure my height at random times during the day over the course of 30 days, I'll probably see something like this where it's going to fluctuate. In other words, what's happening is a little bit of random fluctuation due to, you know, what I've been doing during the day. Was I lifting stuff that would have put compression on my spine? Was I laying down at night, which would have taken the pressure off my spine? And, you know, I'd be a little bit longer in the morning than I would be perhaps at the end of the day when I've been exerting myself or doing something like, you know, working with weights or heavy lifting or something. Okay? So this would occur, you know, anything's going to fluctuate. Anytime we measure anything, whether it's characteristics of a person or it's measuring and doing averages between group, we're going to see something. We're going to see whatever we're measuring fluctuate a little bit. However, if let's say I start having something where this went down to like 5'10", and then I start seeing it, you know, stay something like that, that could indicate that it isn't just random fluctuation or something had happened. Likewise, if you want to try this, anybody that's ever tried or used those inversion beds or those boots where you hang upside down, if you do that over the course of, let's say, a week, and you just measure your height after using, you know, in my case, I'd probably have something like that. And that would correspond to actually having done some kind of manipulation where I change something over and above beyond what you would expect on the basis of random fluctuation. So the dependent sample t-test, the paired sample t-test does this where we take a lot of these within individual measurements, and then we apply some kind of manipulation, and we see what's going to happen next, or whether or not any kind of a difference we had appears to be random fluctuation, or does it appear to be something past random fluctuation? We can say, okay, something has changed, something has significantly changed. Likewise, if I was going to take measures within a group, let's say I'm administering some kind of workplace satisfaction survey. Could do one of those Toddy-esque type things, right? We could look at distributive or procedural justice and see if, on a 20-item scale, how do people rate their perceptions of their work. And if, let's say we had something where, okay, let's say this is engineers, and this is accountants. And within, let me see if I can dig up a little bit darker marker here. Okay, so here's accountants, here's engineers, and let's say within each one of these, if we're going to, we'll just illustrate the observations. So each one of these dashes here is going to represent one person to whom we administered some kind of survey to see if they felt their work was distributive or procedural justice within that working environment. So, say this is 16 points and this is 20 points on a 20-point scale. So we have here's a pattern where the range here is 16 to 20. Now let's say over in accounting, with the accountants we had kind of a similar pattern. It's stuck within that same range. We might conclude that, okay, with respect to being populations, these two populations are the same because on average, let's say they're perceiving procedural justice or distributed justice, let's say 17 here, we'll go with the decimal, 17, and then let's say 17.3 and 17.6. So, kind of the averages would be within that same confidence interval. But let's say something else happened. Let's say we did something where, yeah, come on in. Well, it's good to have an audience. And, shut it back up. You could have just knocked it. Okay. Okay, so procedural or distributed justice scores of 17.3, 17.6. Kind of within that same range. Now, something happened. Let's say we did something to the accountants where the engineers get a big pay raise and the accountants don't. So we could see something happen like this, where the bottom of that range drops, and let's say it dropped down to about 12 for some of those people. So the average becomes, let's say, becomes something like 14.2 or something like that. Now, at this point, we have the parents of two different populations. So if you're going to test for mean differences here, you're going to have differences that are going to be big. You're also going to have the situation where the variation or the range on one of those populations goes well below the other one. Or we could have the same thing happen where, let's say they stuck within that same kind of range, 16 to 20 on some kind of scale, and let's say the engineers were, in terms of their rated perceptions of procedural and distributed justice, we're at 18.3, but the accountants, again, same range, but let's say for them it's 16.1. Okay. So there's another example where we would have means, but the means would be somewhat different. That is, in terms of, would this just be random fluctuation, or would this be, there's actually something that goes beyond random fluctuation here to account for the difference? And of course, with how many 500 years of researching probability, Yeah, real interesting history if you're to dry stuff, but you know, we've been looking at this stuff for 500 years. We've got applied mathematicians, they're theoretical mathematicians, you know, research this every which way since about the 1500s, and then we've demonstrated it by applying what we thought were the patterns to real world data, and so we're pretty confident that we can say that okay, with a certain degree of probability, we can say okay, is this difference really a difference, or is this difference just random fluctuation? Now, what do I do with analysis of variance? Let's say we have a situation where it's more than two groups. So t-tests work really good for two groups, or when it's the same people twice. The other thing that t-tests are really good for are the situations where you have small sample sizes, because what happens with the t-statistics is it continuously distributes, adjusts the distribution for the sample size. So in other words, if you're going to work with n equals 5, you're going to have this kind of distribution. If you kind of think about it a little bit and say that, okay, out here is where the cutoff point is going to be, you know, it's going to make it real hard for something to become statistically significant with smaller sample sizes. With, let's see, n equals 30, you start to see the bell curve occur. And consequently, because cutoff point is going to be somewhere like that, if you're going to try to draw it, it's going to be easier for stuff that comes from differences from larger sample size come up as being statistically significant. And then the other thing we previously talked about is we could have something where it was a statistically significant difference, that is, the differences between two numbers, two or three numbers, or more numbers appears to be something other than random. However, that difference is so small that it doesn't matter, you know, in terms of practical applications. Okay. So anyway, you know, going back into that workplace setting, and let's say you want to know something about turnover, and you have differences in turnover by work group. Well, go out, get those personnel records, see how long somebody has been in a job and what point or how long they're in that job before they leave, and calculate that for accountants, engineers, managers, in other words, let's say, you know, within each one of these cells, let's say you have something like 23 accountants, 30 engineers, and 15 managers. And that's something where you could do that with analysis of variance easily. In other words, you have unbalanced cell sizes, which is going to be kind of a typical for quasi-experimental research. And so I want to know whether or not there's differences in the turnover rate among these three groups. Well, it'd be something you could easily calculate. Determine whether you just had random fluctuation, they were about the same, or if you had a difference between accountants and managers, accountants and engineers and managers. Now, what's happened here? We add one more group onto the analysis. We're going to start increasing the number of pairwise comparisons exponentially. If you had undergrad stats with me, might remember this formula, that the number of pairwise comparisons is also going to be the number of groups times the number of groups minus 1 divided by 2. So I have two groups, it's going to be 2 times 1 divided by 2, so one comparison. If I start adding, let's say, a third group, so 2 times 3 times 2, 6 divided by 2, 3 groups. Increase that one more, 4 times 3, so 12. The 4 groups is going to be 6 mean comparisons. Now go up to 100, or I'm sorry, 10. Let's not go to 100 yet. That's a little bit beyond what I think you should be doing with analysis of variance. That's multiple regression territory. So 10 times 9, 90 divided by 2. So with 10 groups, you would have 45 comparisons. And this is where it starts to become a little bit complex. And at some point, you kind of have to perhaps narrow the focus of what you're looking at, because otherwise the interpretation of this becomes really kind of difficult and unwieldy. the other thing that happens with the null. Say I want to look at mean differences from, two groups, and let's say, okay, the probability that that's a type 1 error, that's just random fluctuation, and it isn't really different, 5%. Well, let's say I compare something else within that same group. Let's say I'm looking at differences with procedural justice. And then I decide, okay, let's take a look at that same group with distributive justice. And we'll survey those two groups and see if there's, how they rank with respect to life satisfaction. So a work and family life balance type measure. And let's say, then I also want to know whether or not they're committed to the employer, commitment to employment, and that comes up as significant, 0.05. Now, the probability of them all coming up as significant at 0.05 is probably very small, but the idea with this is I'm going to make this real simple in terms of explanation. What happens across, if I'm just doing t-tests here, is this is going to sum up to 0.20. So there's a 20% probability that at least one of these is going to be a type 1 error. Okay, that this is an erroneous conclusion that there really is a difference. Now, this would be doing 4 separate t-tests. There's a procedure that you can do to use 4 separate t-tests. We'll talk about that with the post hoc test tonight. It's called the Bonferroni method. And basically what I would do is, if I was going to do this number of t-tests, what I would do is look up whatever the alpha level was, or the t-statistic, that would divide this value by 4, so adjust it for 4 comparisons. Well, just as easy to run analysis of variance, because what analysis of variance will do is tell you whether or not there are any differences here, and it will control for all this. What this is called is either compound, or a lot of people say family-wise type error, often abbreviated FW. Compound works. The idea is that you do multiple t-tests, you're going to add up those p-values to know what determine what the true value of getting, the real probability of getting a type 1 error is across 4 t-tests. Analysis of variance, 1 analysis, you're done. If it doesn't come up, if the overall F ratio doesn't come up as significant, like rolling on the scene of an accident, if the police officer says nothing to see you're moving, well, it doesn't come up as significant, we don't go back in and take a look at the data. However, if it does come up as being significant, then what we do is we go back in and we perform. We'll talk about this a little later, post hoc tests, that's after the fact tests. However, there's other tests that we can use that are called them a priori tests. And the difference here is with post hoc tests, the data comes up significant, then you decide, okay, this is what we want to look at. We'll use tests to examine that data. Now that we've seen significance. A lot of times with the a priori test, you're planning that comparison ahead of time because you have some kind of theory or rationale that says that that the data should come out a certain way. Now the difference here is with a priori tests, when you have theory, so somebody came up with a good rational explanation as to why the numbers you're looking at should come out a certain way, or previous research has demonstrated this, or you've got really good, strong logical rationale where you're just kind of expecting this. Well, if that's the case, these tests tend to be a little bit more lenient than post hoc tests. In other words, if you're going to decide after the fact, the ethical thing to do is to make that test a little bit more stringent. And when we do these post hoc tests, for any of you that have had class with me before, you worked with SPSS, as post hoc tests are listed in the analyses menu, and I think there's like 14 tests total in SPSS. Actually, I've been counted since SPSS 22. But the idea is you have these 14 different, if you want to say, flavors. Well, the difference in those flavors is how lenient or how strict they are with respect to coming up significant. And again, some of this also comes back to, is it worse in terms of what you're looking at? to incorrectly reject the null hypothesis. I'll give you a plain English explanation, false positive. Is it worse to have a false positive? That'd be your type 1 error. Or type 2, false negative. Okay. So, previously, we're talking about medical testing. If you're going to get tested for cancer, you're going to get tested for strep, you're going to get tested for HIV, you're going to get tested for hepatitis, Lyme disease, or whatever. It's better to have a false positive with that first test, because then you can also go back and screen and see if, with a different type of test, and see if it comes up the same way. On the other hand, if, let's say, what's going to happen is you're going to end up committing workplace resources to re-engineer jobs or buy capital equipment, you have a false positive. It can push costs up without producing any kind of result. Okay, so a lot of times, depending on what we're looking at as applied I/O people, probably if it's like committing more resources, multiple tests to see if whatever you're suggesting is going to work, to see whether it kind of leans towards positive or negative. False negatives, if you're going to, are probably going to be less harmful if it's only going to be one examination of data or one test. In other words, you're not going to commit organizational resources to something where it isn't going to produce a result. Again, a better approach to this is to examine stuff a lot of different ways and borrow a term from Tillman, kind of converge on a solution stuff. Okay, so enough of that. Let's get to the real fun of the PowerPoint presentation. Okay, so multi-sample inference, analysis of variance. Now, fancy way of it, just saying, okay, we're going to test multiple groups to see if there are differences among those groups. I just keep things organized here. Some learning objectives. Well, at a minimum, after this week, see if you're able to explain analysis of variance. If you didn't already know how to explain it, the rationale. We'll talk about that in a minute. Comparing experimental designs. We'll talk a little bit about randomized blocks and completely randomized blocks and factorial design. A lot of these terms are going to pertain sort of towards experimental research, but you can use some of the stuff if you're doing some quasi-experimental research, especially if you're doing something like examining whether or not certain training programs work, or if you're examining whether or not certain types of tests predict job performance across different jobs. Now, this idea here, factorial design, what that means is we're going to take and we're going to mix up independent variables. We're going to have more than one independent variable. So I'm not sure why they decided on this, but when you're talking about more than one independent variable in ANOVA, it's called a factor. The factorial design means that we're going to have more than one independent variable. So going back to the example that I threw on the board before, if we're going to look at differences in perceived distributive justice or procedural justice by engineer versus accountant, we could also add another independent variable. We could say, okay, does it differ by gender, or does it differ by whether the person's over 40 or under 40, or anything else that we think might be meaningful to try to interpret differences on a more finite level. So analysis of variance. One of the trick questions we used to ask the doc students on their comprehensive exam was, explain why it's called analysis of variance. Trick question in that they all knew analysis of variance, but at some point had forgotten that, what specifically was happening with the process, or they thought we're trying to trick them and made that way too simple. Analysis of variance technique takes, and the term that's often used is partitions. In other words, it's going to take all the variance and it's going to identify where that variance is coming from. So whatever's making those numbers move, up, down, whatever, it's going to identify the source of what's causing that movement based on your independent variables. So total sum of squares of deviations above the observations. So again, plain English, all the movement that's occurring within those numbers and tries to figure out which ones are associated with independent variables and what proportion is associated with error. Now again, error doesn't mean mistake. We're talking about research design. What error means is all that random stuff that's out there that influences whatever we're working on. Another way of putting it is the effect of all those potentially infinite variables out there that you're not looking at as part of the study or using it as an independent. So, factor. Categorical quantity under examination of the experiment is a possible cause of variation within whatever response variables. Now, plain English. What group? So basically what you're saying is your factor is going to be defined by whatever you're grouping participants by. The example that I gave previously, accountants, engineers, and managers, okay? That would be one independent variable. And we could call it independent variable job type, and it has 3 categories or 3 levels. Part of what we're doing with that was seeing whether or not being in any one of those 3 jobs influenced your perceptions of procedural justice, distributive justice, whether you were happy with the job, whether any of those groupings might be associated with, you know, people calling in sick or how long they remain with employer, whatever you're interested in. So we would examine whether or not those groups, and in our case, we have to be careful with cause, but, you know, as applied IO people, we say, okay, are related or associated with. Possible cause, yeah, possible cause in people that, let's say, for example, we found lower perceptions of procedural justice with the accountants. Well, is it possible that being an accountant is causing that? Yeah, possible. But, you know, here's where we're going to differentiate between what we would do in true experimentation. With true experimentation, you've assigned people to conditions, so you have not you're not looking at possible effects of pre-selection. In other words, is it possible that people that are less happy or less likely to be fussier about justice, are they more likely to go into it? Well, nothing positive, but again, we could all say that, well, this is associated with this grouping, and therefore, here's some things we might want to consider to try to change the perception, or try to change whatever it is that we're attempting to measure. Now, levels, again, I think where this gets sort of confusing is we're used to thinking of levels as being hierarchical, and that isn't the case with ANOVA. Levels just means that they're different groups. It refers to categories, measurement strata of a factor of interest in the experiment. Now, with that example I gave before, job type in 3 levels, 3 different groups. Yeah, if you really want to see this illustrated, if one of the levels is going to be gendered, you have men and women, that's, you know, unless you're sexist, that's not going to be anything where you're looking at it hierarchical, just that it's a quality of it. Now, having said that, the other thing to keep in mind is that we're going to talk about this in terms of nominal, ordinal, or integral, or ratio. In ANOVA, the independent variables are going to be nominal, they're going to be groupings. So was there a difference between group A, difference between group B, group C, between A and C, between B and C? So some types of experiments, if you could do them, completely randomized, one-way ANOVA, factorial, and randomized blocks. Now, we can do things with randomized blocks as a research design in applied settings, especially if we're looking at whether or not different types of training work or different types of workplace environments lead to higher levels of productivity or satisfaction. With the randomized design, this would be Dr. Walson. Experimental units. Okay, how's this for dehumanizing people, right? Subjects. So if you're participating in research, you're not a person, you're an experimental unit, or assigned randomly to treatments. Actually, the APA kind of prefers that we just refer to people as participants now. Subjects are assumed to be homogeneous. Well, basically what you're saying with that is that with whatever it is that you're looking at, if you're going to try to experiment, you're assuming that people are going to be roughly the same within a certain margin of error within a certain interval, whatever it is. One factor or independent variable, two or more treatment levels, one groups. Now, we don't usually do treatments in applied organizational research unless we're adjusting an environment or whether or we're working with some kind of training. What we might say instead of treatment levels is we might say, one or more groups of interest based on whatever it is. Now, in this case, if it's just one type of independent variable that exists at more than two levels is being analyzed by one-way ANOVA. So that example with, again, with the accountants, engineers, and managers, that would be a one-way ANOVA, that'd be a 1 by 3, one independent variable by 3 levels. The equality of two or more population means. Again, what that's saying is that your populations are going to be defined by your groups. If I have engineers, managers, accountants, those are going to be 3 populations in terms of how I define populations of interest, or I want to see if there's some kind of difference. So the idea is the means that are generated by those groups, are they the same within some kind of random fluctuation, or are they past that to where we're going to say, okay, the possibility of this being random fluctuation is 5% or less, so that I give a p equals 0.05 or less would be the threshold that we would use to try to determine whether or not something was just completely random. Now, there's nothing magical about p equals 0.05. That's a convention that was adopted late 19th century by people who were doing, what was then the forerunner of psychological research. We could set it lower, we could set it higher. Moses didn't come down from the mountain with that on a stone tablet. It wasn't on a third tablet that he dropped or anything like that. It was just something that was adopted because it just kind of made sense for people to do that. Now, if I want to set that lower, instead of 0.05, I want to set it at 0.01. That could be because I want to really reduce the probability that whatever I'm going to conclude is going to be a type 1 error. So 0.01 would mean there's a 1% probability that that difference is going to be just random fluctuation. And I could set that even lower if I wanted, 0.001. But the problem is the lower you set it, the harder it is for something to come up as being statistically significant. So again, you have to think about that, the trade-off between do you want a false positive, do you want a false negative. So variables with one-way ANOVA. Actually, we could say the same thing with factorial ANOVA too. Nominal independent variables, groupings, different categories. Okay. And continuous dependent variables. In other words, something where it's either interval or ratio level data. Now, having said that, I've mentioned this before. When we work with Likert scales, even though they're kind of ordinal, that is, how strong is your feeling on whatever it is I'm asking about? Does you strongly agree, strongly disagree? Again, not equal units, but we'll still use that as if it's interval level data because we can calculate units off of that and interpret the data in ways for them to do. So one-way ANOVA assumptions. Randomness and independence of errors. So basically what we're saying with that is if anything is truly random, it should be random. It should be independent. If it correlates with something else or those errors correlate with each other, it isn't really error. So in other words, we're assuming that if it isn't variance that we're looking at, if it isn't differences we're looking at, it's going to be, random fluctuations, kind of pushing the numbers. Normality. So in other words, if I plot the data out, well, it kind of look like a bell curve. Now, ANOVA tends to be fairly robust with respect to violating that assumption of normality. In other words, if it wasn't a perfect bell curve, it'll still be okay. The more the data, or the less the data resembles a bell curve, the harder it is going to be for it to come up as being statistically significant. The chances are, if you violated assumptions with ANOVA, it's going to lead you to a dead end. Homogeneity of variance, so populations have equal variances or fairly equal variances. Now, if they don't have equal variances, in other words, I've got some examples in presentation that I'll bring up a little bit, but Slide back over the board. Let's say, here's the distribution of one group, and here's the distribution of another group. Well, if those variances aren't equal, it's going to lead to the conclusion that there's statistically significant difference between groups. Okay, so don't get scared by all the Greek script here. This thing here, this is the Greek letter mu. It's the population mean. And hypothetically, what you're talking about with ANOVA, if in H0, the null hypothesis is correct, no difference than what you're saying is mean 1 is equal to mean 2, mean 3, however many means you have. That basically within the limits of random fluctuation, all those means are going to be equal. Consequently, if you were doing something like a treatment where you're, let's say, presenting a treatment example, an implied setting would be like presenting Microsoft Excel training. And you want to see whether or not people that got training package 1 were different than people that got training package 2 and 3 versus people that had no Excel training. That would be an example of a treatment. The alternative hypothesis, not all the, and again, mu, and the J stands for all the different groups you have. In other words, J could be anything from like 3 to 103, depending on how many groups that you have. At least one population mean is going to be different. So in other words, one of these is going to come up as being different from the other. That's all it takes with the numbers. Just one of them out of all of them to be different before you see you have a statistically significant. So treatment effect occurs, and so consequently, all the population means, all the means from all the groups aren't going to be equal within the limits of common error. Any difference, whether it's one group or all groups being different from one another, is going to exceed normal random probability. So this is what I was saying. I would have some slides that would have the example. So, example where the alternative hypothesis is correct, all population means are equal. We've got 3 groups, if you can see the colors here, and the mean for 1 equals the mean for 2 equals the mean for 3. This is kind of a good hypothetical example because in this case, the distributions pretty much look the same. However, the alternative hypothesis, not all means, and J again, denoting how many different means you have, in this case 3 means, at least one population mean is going to be different out of the 3. The treatment effect, and again, nothing's equal, so you have an example here where, in this case, looks like mean 1 and 2, or the means from group 1 and 2 are about the same. However, the mean for group 3 is different. Yes. I think I got it. You didn't do anything. Okay. Just check the battery. Sorry, all the power supply came loose. Yeah, still streaming. And it's charged. Okay, we're good. It's like
nothing to wake you up like a scare.
What's that?
Is it nothing to wake you up like a scare?
Yeah, well, at least it gave you a warning that the battery was getting low. So one way to know the basic idea compares 2 types of variation to test. Equality of means. In other words, and the 2 types of variation here, we're talking about comparing variation that's due to whatever our groupings are or whatever it is that we're manipulating to how much variation within that set is just random fluctuation. Again, going back to one of the earlier slides, we're talking about the process is taking all that variation, all that movement within the numbers and trying to figure out what the source is. So breaking it down again to how much variation is due to random fluctuation and how much of that is due to real differences between groups. Okay, so treatment variation is significantly greater than random variation, then it means things are not equal. So if you had a situation where, let's say, the random fluctuation equaled 100 and between group variation equaled 100, you wouldn't have anything there because then you conclude that 1-to-1 ratio And that's literally, literally what the F ratio is taking the variation that's due to whatever the independent variable is and dividing it by the random fluctuation. So if it equals 1, you know, you don't have anything there. On the other hand, if it was a situation where the variation was due to the independent variable was 500 and the variation that was due to random fluctuation was 50, you'd have a ratio of 10, and that very likely, depending on how large the sample size would come up as being statistically significant, or you'd say you'd have a whole lot more. If you think about this in kind of relative terms, you would have a whole lot of movement or fluctuation in those numbers that was due to the independent variable versus just random fluctuation. So, variation measures are obtained by, again, by partitioning, by saying, okay, here's all the variation, and this equals so much random variation plus variation that's due to variable 1, variable 2, variable, however many variables you got. So, you know, kind of a full circle with that, an F ratio literally is a ratio. So, and the other thing, you might have heard the term general linear model. Basically what's happening is you're saying, okay, here's all the movement, all the wiggle room, all the shape, all the whatever's going on with respect to how those numbers differ from each other, and it equals source 1, source 2, source 3, source j plus randomness or error. So let's talk about that a little bit more. One-way ANOVA partition takes the total variation, and again, we can talk about that as movement in numbers, and decides how much of that is due to treatment or is due to independent variables, and how much of that is just due to variation due to random sampling. Now again, the idea of random sampling, if you measure your height or weight every day for 30 days and you do that at different times of the day, that's going to be a random sample. And that's also going to determine whether or not, you know, you weigh, in my case, I think I mentioned this before, I can vary about 2.5 pounds either way from, okay, my mean weight, so I've got it calculated, is 194, so I can be as heavy as 196.5 if I've had a big meal and you know, chugged a bottle of, like a liter bottle of water, to as low as 190, let's see, 91.5, I think is low. Again, random fluctuation. Now, if I weigh myself or measure myself at the same time every day, I'm not going to have it. So variation due to treatment, sum of squares among, sum of squares between, sum of squares treatment, among groups variation. These are all going to be the same, mean the same thing. And this is where it gets kind of confusing too. It's kind of like with the t-test, we could call a t-test where the same people get measured twice. We could call it a repetitive sample. We could call it a repeated sample. We could call it a paired sample. We could even call it a correlated t-test. They're all going to be the same thing. Sum of squares within, sum of squares error within groups variation. In other words, differences that aren't, well, the numbers aren't coming from between groups, but we're finding kind of the same pattern within groups. And again, all these things mean the same thing. I usually go with this one here if I'm explaining stuff, the sum of squares error, with the idea that if you explain that, tell people what you're talking about is random fluctuation, not that a mistake was made. I think that one makes the most sense. Now, here's an example drawn out. This is what I was doing previously on the board. Sum of squares total. And basically we have here is sum of squares, so observations within group 1 divided by the mean and squared, sum of squares for group 2 and sum of squares for group 3. Now, you know, this is a little bit harder to picture than this. In other words, if you look at what's happening here, this is the overall mean if you average across all 3 groups, this line right here. So what's happening here? You kind of see that these groups are scattered different places. So in this case, you would probably have a significant difference here. Certainly would probably have one between group 1 and group 3, and most likely between group 1 and group 2. Now, if the numbers were big enough, it was a single observation down here, group 2 and 3 might be come up as being roughly equivalent or significant. So, treatment variation, group 1, group 2, group 3. So we're looking at the number, and basically what we're going to do is we're going to, with that variance, what we're doing is the variance, if you're interested in this stuff, it's a pretty simple concept where you're taking and you're squaring each mean difference. So in other words, you're taking each observation, you subtract the mean, square the difference, and then divide it by the number of observations. That's a simple variance. What it is the average squared distance. For those of you who are fans of Euclidean mathematics, the average squared distance is represented with some kind of a data set. Now, if you put, let's say you take the square root of that, you get the standard deviation. Random variation. In other words, what you're looking at here in terms of random variation, if you look at the arrows here. In other words, here's the mean within each one of those groups, and how much does it fluctuate within each one of those groups. So this would be the variation that would be used to determine whether or not you had more variation that was due to independent variable, or it was just sort of random fluctuation that's occurring within the groups that explains most of the differences or all of the differences. So the statistic here, let me put this in plain English. This is what an F statistic is calculated from. Now, MST means mean square treatment, mean square independent variable, divided by mean square error, mean square random. And to arrive at those calculations, what you do is you take and subtract the mean from each observation, and you square it for the whole for the treatments, and then divide by the number within the number of treatments. So in that example here, where we had 3 groups, this would be p minus 1 or divided by 2. Now that's something that's called the degrees of freedom. We look at all the variation for the all the sum squares. We would divide by the degrees of freedom to come up with a mean square. Same thing with the error term. So we would take the overall mean, we'd subtract each observation with the overall mean, we would square that, add that up, and then divide by n minus p, or the total number of observations minus the number of groups. That would be the degrees of freedom. Now, the degrees of freedom are how many different ways within a group of numbers can numbers vary. And kind of what you have to do to answer that question is you have to at least take one number and use it as an anchor. In other words, 3 groups, how many different ways can 3 groups vary if you use one as an anchor point? Well, there's 2 left over. Likewise, with the overall numbers, another way of getting this is to look, add up the number of groups and subtract 1 from each group. That'll get you the same number. Basically, what you're trying to do is you're trying to figure out, okay, what's the average amount of error that's due to treatment? I'm sorry, variation that's due to treatment, and the average amount that's due to error or randomness. We'll expand on this a little bit later. We'll talk about this with some of the applications we're looking at, data sets in use SPSS or JASP. Partitioning sums of squares. To identify the source of where the movement's coming in the numbers, treatment, independent variable, and error or randomness. So number of groups minus 1, and again, 3 groups minus 1 is going to equal 2 with that example we had previously. Or what's the total number minus the number of groups? And again, another way of getting that is to just take 1 from each, subtract 1 from each group, and just sum all that out. Now it's going to get a little bit convoluted. We're talking about groups where they have different sizes, and we'll address that a little bit later. Part of what we do with that is we'll use something called the harmonic mean. Now I'm not going to have anybody calculate the harmonic mean to calculate the weights, but the idea is there's a special type of mean that gets used by the software to be able to adjust that for different cell sizes. Then, so a variation, divide by the degrees of freedom, produce the mean square. The error, take that variation, divide by the degrees of freedom for error, get the mean square, and basically what we're doing is taking the mean square for treatment and dividing by the mean square for error to say that, okay, here's the ratio of randomness versus ratio of randomness to the amount of variation that's due to whatever it is. Now, at this point, what we've done, if it comes up as statistically significant, is we don't know where the differences are. If it comes up as statistically significant, we know that somewhere among however many groups we have, there's at least one statistically significant, that is one difference, that is a difference that's not just random fluctuation. Now, the t-distribution, I drew a bell curve. The F distribution isn't going to be a bell curve because the F values can only be positive. And this is what's sometimes called a Poisson distribution. The idea is Poisson is the French word for fish. I'm probably mispronouncing it really badly, but I'd have to go to New Orleans to take French lessons to pronounce it correctly. If you use your imagination, this kind of looks like a fish, so put a tail there. Actually, with very little imagination, you can kind of imagine that as a shark fin, if that helps. So, which is sort of how people picture statistics. Oh no, here it comes. It's time to get out of the water. We have here is there's going to be one of these distributions for each set of degrees of freedom. In other words, with t-tests, we only have one set of degrees of freedom. Typically, the number total minus one. If we're doing something with paired dependent sample t-tests, we do the total number of observations minus 6. With ANOVA, we have one set of degrees of freedom again for the number of groups, and then one to kind of represent the number that we use to calculate random variation. So you can see a different distribution like this, again, for each type of ANOVA, whether it's one way with 3 levels, whether it's a 2-way with 3 and 4 levels, be a different distribution. Actually, you're only going to use this for two sets of degrees of freedom. We'll get into that complexity next class. And what is here is something called a critical value. So if you were to look this up in the back of a textbook, you're not going to see this, but what you'll see listed is it perhaps a table where it says, okay, here's your degrees of freedom, and here's the value that equals. So what you're hoping for is that if, let's say, you want that to be statistically significant, it's going to hit this value, it's going to be that value or greater to be significant at whatever the pre-chosen level of significance. And that's what that alpha is. Alpha represents probability. Alpha could probably kind of confuse it because we use it for a lot of things, but in this case, the alpha level is going to also be the level at which the results are type 1 error, or the results at which it's a level you see that's statistically significant, which again is the level where you're saying, okay, it's either non-random, or if it's random, it's real small random, it's 5% random or less. Okay, so example here. Epidemiologist, so you have 3 food supplements yield different milk yields. So this would be example where you were using livestock. Okay, so there's food 1, food 2, and food 3. Now, this is kind of a familiar example to me, having gone to high school in Wisconsin and understanding that, okay, these would be like pints of milk produced per cow per day. In other words, there's a different food supplement yield a different milk value here. So if you look at the numbers, you can see differences in the numbers, but the question is, are these differences just kind of random fluctuation, or are there really differences? So solution. Alternative, null hypothesis, all 3 are equal. Alternative hypothesis, all are not equal, but there's a difference in there. E1 equals 2 and degrees of freedom 2 and 12. Critical values here, in this case we have, and this would be taking that same data and calculating how much of that was randomness and how much of that was real, appears to be real difference in the numbers. We end up with dividing that by that to produce the 25.6. And going to this example, what we had to do with 2 and 12 degrees of freedom was it had to be at least 3.89 to be significant at 0.05. So the idea here is 25.6 greater than 3.89, and we don't even have to count on fingers to figure that one out, right? I don't have to. So yeah, the answer 25.6 greater than 3.89, so 25.6 would be way down there. So consequently, we have a significant difference here. The conclusion is, population means are different within that example. Again, the populations here would be defined by the three different groups getting a different type of food supplement. So break that down, food and error. And this is what if you're to run this in SPSS or JASP or any other program, this is what it's going to break it down into. So 3 groups and 15 total. So 15 minus 3 groups, or 3 groups of 5 and take 1 from each group, you have the same number. Now, sum of squares. How if we take and we subtract the mean from group 1 from group 2, and the mean from group 2 from group 3, and the mean from group 3, 1 and 3, and square those and add those all together, we're going to get 47.164, and we divide by the degrees of freedom. So 47.164 divided by 2 is going to get the 23.582, and with that error, 12 degrees of freedom again, 15 total participants or subjects within the group minus the 3 groups, or 5 groups of 3, subtract 1 and multiply by 3, you're going to get the 12. And this would be taking and subtracting each observation from the overall mean for all the observations, the grand mean, where that divided by 12, and that's going to give you the 0.9211. Now the last step here, take that, divide it by that, and that's going to give you the 27.60. Again, what's happening down here is that if we've done this correctly, what should happen if you were doing this by hand or with a handheld calculator, one of the ways of checking to make sure that you did it correctly is you calculate this and then make sure that these other 2 calculations added up to be whatever it is that you derive when you're doing those parts of the equation. In other words, did you identify the sums of squares correctly? Well, 2 and 12, or if you look at the total observations minus 1 should add up to be 14. And this should add up to being that. Now, what do we do with this? Interpretation. We don't really do anything. And again, what I would consider a holdover from those days when you needed a computational check, because you'd be doing this either with very simplistic software or doing it with a handheld calculator. Now, I'm told that in the Psych 300 classes, the first undergraduate stat classes, what happens is people are asked to do this by hand, and that's what I had to do it by hand with the first stat classes I had as an undergraduate. I should say by hand. By the time we got into the second class, we were allowed to use a calculator. I think what that does is, if nothing else, it helps you understand what's happening with this formulas. The days when they had to do the stuff by hand, typically what they would do is they would have 2 people working independently on the same data set to make sure they came up with the same conclusion and then conclude that it wasn't an error. So if you're going to do it with a handheld calculator, that makes sense. Kind of an extension of that, when I was early career working for the Center for Business and Economic Development in Montgomery, Alabama, if we were doing something that involved testing or something that was fairly high stakes, we would have 2 project teams working on the same data set. One team would do it in SPSS, and the other team would analyze the data using SAS, and if the results came up about the same, then our boss would say, okay, well, hopefully we've got this done. On the other hand, if there's a discrepancy, we'd have to go back to square one and start all over again because we got all messed up. That rarely happened. For no other reason, it's because you don't want to have to keep doing this stuff over and over again, right? So pairwise comparisons. If the null hypothesis is rejected, it can be done with adjustments for type 1 error, pairwise comparisons, whether they're planned in advance. If they were planned in advance, as we said before, if it was an a priori planned comparison, then we can use a test that's, or it's acceptable to use a test that's fairly lenient. Now, the example here, if you've looked in SPSS or in JASP, you'll notice that one of the tests that you can use to compare the means of something called the LSD test. You know, if you like drug humor, insert your own joke here. I've heard all the jokes over the last couple of decades, so I'm just going to know if this is a difference test. I think it was a generation that was ahead of me by about 50 years, as people that grew up in the 60s who would have thought that was a whole lot funnier, you know, like the hippies, that generation, than what I found. Yeah, for those of us that grew up, or you know, went to high school someplace close to a shoreline someplace, chances are LSD, what LSD meant to you was Lakeshore Drive or something like that. So there's a Lakeshore Drive in Chicago that I've been on, and a Lakeshore Drive in Milwaukee. If you all know who Derek McDonald is in the doctoral program, he's from Chicago, and they use the line when they would go out and drive on a nice day on Lakeshore Drive in Chicago, that it was typical to say they were going out tripping on LSD without any, you know, being part of any kind of controlled substance subculture. The type 1 error can be adjusted if other comparisons were not planned in advance. Now, von Ferroni's test means that we're going to take the number of comparisons to try to figure out what the obtained coefficient should be. In other words, you're going to say, okay, we didn't plan these comparisons, so we're going to have to take that coefficient, we're going to adjust it to make it higher, so it's more difficult for our unplanned comparisons to come up as being statistically significant. Consequently, we're less likely to make a type 1 error. The Chaffee's test, this is one I use quite a bit. And the reason I use it is a lot of times I'm working with data where I don't have theory, where I want to know if there's a difference of some kind, and I'm hypothesizing there might be a difference without specifying why it could occur, other than some people were accountants, some people were engineers, some people were line employees, some people were managers. For those kind of comparisons, Chaffee's test tends to be one of the most conservative tests to do some kind of pairwise comparison after you've completed the event. Now, if you've worked with SPSS or looked at JASP, you've seen it. So compare level 1 and compare level 2. To kind of summarize this in plain English, you're creating confidence interval. And maybe that isn't plain English, but you're creating a confidence interval to say that, okay, if there's a mean difference here, you're going to take a look at means from two groups. You find that mean difference. You can construct a confidence interval, or you can do an error term, like what we do with t-tests, where we calculate, okay, at what value do two values become, or two different means become significantly different. So that's what's happening here. You're calculating mean square error for group 1 and group 2, and saying, okay, if that mean difference yields a ratio, you know, ratio t that's past a certain level, you're going to say, okay, there really is a difference. Because at this point, again, if the F ratio comes up as significant and you have 5 means in there, you don't know until you do this which of the 5 are going to be statistically significant. Now, to go back to that n times n minus 1 divided by 2, you're talking with 5 means, you're talking about 10 possible pairwise comparisons. So you can have 1 as being different, you can have all 10 as being different. All you know with the F ratio is something is different there, and you need to get back in. So comparing level 1, comparing level 2, and adjusting that significance level, that should have been maybe a different color than red. Adjusting a new significance level to fit the comparison between the two groups. Now, what are you going to do with this with respect to the stuff we're going to do it here? Nothing. This is what's happening, that the software is going to do this for you. In other words, what that software is doing when it says that there's a difference between two means, and usually how it tells you that is it'll put an asterisk by that comparison. So 1 asterisk means significant 0.05, 2 asterisks means 0.01. So 1 asterisk, 5% only 5% probability that's random, 95% probability there's a difference there. 2 asterisks, 1% probability that's random, 99% it's something there. So an example of typical output, least square difference test. This could come from SPSS. This could also be something where it came from like SAS. If you've worked with the JASP, if you've messed around with that a little bit, you've noticed it really neatly formats any of the output in a format where you could take that, you could copy that, and you could move it, just drop it right into the paper. It's already APA format, which is nice. That doesn't always happen with SPSS. APA has been kind of lenient with SPSS, or us using SPSS, and saying that, okay, if you want to just copy and paste that SPS output and label it with APA format and labels, then be fine. If you're working with R, I don't know if anybody's worked with R. How do you have to do that?
I've messed around with it.
Yeah. What's nice about R is you can tell it exactly how to print stuff, how to format the output, but it doesn't automatically give you the output in APA format. So, plus side, very flexible. Very flexible if you want to design output, very flexible with respect to reading data. Flip side is it's going to take a little bit more time and effort than something like JASP, where you can just run, take the graphic, the table, whatever it produced, just take that, copy it, put it right into your document. Now, with respect to APA format, we stress that a lot in psychology. However, for people that are working in applied workplace settings, chances are you're not going to use the APA format to construct the whole document, but with respect to reporting results, it's pretty typical. I mean, it isn't just us that use it in psychology, it's doctors, it's nurses, it's people in engineering. It's sort of become, with respect to how to format data, it's kind of become the universal standard. Anyway, what I'm saying is, if you graduate without having mastered APA format, or writing a whole document, that might not be fatal. On the other hand, with respect to being able to present data or embed data in the document, it's the one acceptance. So, t-test here for that difference. Now, t-test, again, this is based on the idea of students T, where we're going to compare one mean to another mean, or more specifically, we're going to subtract one mean from the other mean, get the mean difference, and we're going to divide that mean difference by what we think is the value of random fluctuation within that data, and that produces the t-statistic. And the t-statistic, like the F statistic, these are what are called table statistics. In that by themselves, if all you had was that number and you did not have anything to tell you whether or not it was significant at 0.05 or 0.01, it's pretty much meaningless. So what you do is you go to the, and this is how it came, this is why it's called table. Historically, people would have to have printed tables where they would calculate the statistic, then look at that table with the degrees of freedom and determine whether or not, based on that, based on the calculations of previous mathematicians, did you have something where it was either high probability, which is random, or very low probability. Now, the least square difference test, one of the things it's doing is it's controlling for the number of comparisons you make. In other words, that example that we talked about previously with the t-values, if you do a bunch of t-tests, you have to sum the alphas up, and that tells you overall whether or not you have at least one type 1 error in there. The least square difference test is going to be calculated to account for the number of comparisons you have, so consequently you're not going to get in trouble with this. Now, again, these tests are going to vary in terms of how stringent they are. That least square difference test is one of the simplest tests that's out there. If you had planned comparisons, if you have theory or strong rationale to say, okay, this is what we're expecting, and if the F ratio comes up this way, then we're going to go back in and examine for mean differences with the least square difference test. Yeah, based on strong rationale and theory, you'd be justified. The other hand, if you're going to operate like I do on a lot of occasions, where it's a matter of going into an applied setting, gathering the data, I didn't assign anybody to groups, I don't know anything about the distributions within those groups, so consequently I'm going to try to err on the side of caution. I do that with everything I do with something where it's going to lead to some kind of organizational change. I want to be real cautious and be real stringent with respect to not creating a type 1 error. Now, if it was a different example, this is something you're not typically told to do in stats tests, to inflate type 1 error. However, I do inflate type 1 error if I'm looking at something where, I'll give an example, something I was working with today. I was looking at the New Orleans Police Department test and looking at the items, and looking at whether there's differences between men and women, or white, African American, Hispanic, Latino, in terms of item scores. So looking at those differences and saying, okay, is there a possibility there's a difference here? Well, in that case, what I did was I did a bunch of unadjusted checks with fairly lenient statistics, with the idea that if there's a difference in here, and it means we need to review this test or parts of the test or items with subject matter experts to make sure that they're not biased and they're actually measuring things that are related to the job, that's when I play type 1 error. Okay? So the stuff that the Tillman Sheets and I do when we're looking at test data will go in the opposite direction of everything you've ever been told statistics about, not playing that type 1 error. Now, again, looking at, I'm going to complete the slide before I move on. Here's your mean differences. Okay? So I should say means. Here's the means: 20.59, 22.61, 20.93, and what we've determined here, what the least square difference test says, is that for something to be different, if we subtract this number from this number, it has to be greater than 2.17881. In other words, there's your critical value. Now, in this case, you're going to notice that we have at least one difference where that's correct. So, another example, using SAS output, bond Ferroni. Now, this could also be SPSS output or R output. Here's the alpha level, 0.05 degrees of freedom, mean square of error, critical value of the T. And that's the one we're going to take a look at. It's a minimum significant difference. And in this case, if we subtract, the means with the same letter are not significantly different. So if we subtract one mean from the other, we compare it to the critical value, it tells us whether or not we have a true mean difference. So if that's still sinking in and it's not making sense, no worries. We're going to keep going over that stuff. One of the reasons I took the deep dive into ANOVA tonight was let's start off with the difficult stuff up front and have chances to work with it again and again until it becomes sort of second nature. And again, with respect to ANOVA, that's something I do in workplaces. Again, anytime you're trying to evaluate whether or not the difference is occurring within groups, it's a very useful procedure. The other thing that's good about that for those people that are applied researchers is what we said in the beginning about ANOVA being fairly robust with respect to violations of assumptions of normality. Most of the data that you're going to end up working with, or I should say most, a lot of it is going to be, it's going to depart from normal a little bit. In other words, give you a quick example of that. This is probably how the thing came out. Let's say I was looking at whether or not people were satisfied with their jobs. Here's the score on some kind of satisfaction survey from, we'll make this 1 to 20 or 0 to 25. And kind of what you're hoping for is that by and large, most people are going to be satisfied. So let's say here's the engineers, and here's their scores. Okay? So consequently, where you see this kind of really start to climb upwards would be somewhere around, let's say 17, something like that. Now, not a normal distribution. Kind of normal in that if we were going to say, okay, if we could extend this out further and we had a point of diminishing returns on here, what would happen is that would kind of turn into the bell curve. But still usable for the purposes of ANOVA. Now, let's say here's the manager types. Let's say they had something like that. Now, again, not a complete bell curve, but fairly normal. And the idea is to determine whether these two means are different. Well, if it was just the two, we could do a t-test. However, let's add another one in here. Let's say these are line employees. And yeah, normal or reasonably normal for purposes of testing analysis of variance, but not a perfect bell curve. Now, again, if you violate the assumptions of not having a perfect bell curve, which is not what I draw. This is another reason why I'm not a graphic design person or an illustrator. But yeah, okay. So you don't have that perfect bell curve. ANOVA will still work in applied settings with real-world data. It's just that the more you deviate from having that bell curve, the harder it is for it to come up as statistically significant. So what I typically tell people is this is one statistic that's not likely to get you into a lot of trouble. if the data aren't amenable to that kind of analysis. Randomized blocks. Okay, so we'll take a trip into Walsick land here. So if you're Dr. Walsick, you're doing the lie detection research. You have 100 people show up, so you're, again, experimental units. Right? Participants are assigned randomly within blocks. Blocks are assumed to be roughly equivalent. Now that, with homogeneous, it doesn't mean that they're going to be perfectly identical. Identical means that they're going to be, fairly close or about the same is how I would interpret that for flight settings. One factor, independent variable of interest, 2 or more treatment levels or conditions. If you're Walsick, you might have condition if you're doing the lie detection research, tell lies, tell the truth, mix it up a little bit. So there'd be 3 different conditions. And people would be randomly assigned one of those. That is, anybody that could come in, anybody that came in had equal probability of being assigned any one of those conditions regardless of that. Now, one block is that. In other words, randomly assigned 2 blocks, randomly assigned within blocks. Blocks are assumed to be, again, homogeneous. One blocking factor. We'll illustrate that in a minute with the graphic. So, you're dividing people into blocks, and treatments are randomly assigned within blocks. Now, this would work really well if, let's say, you're going to repeat something across people. In other words, I was Walsick, and I'm going to say, tell extreme lies, tell small lies, sort of tell the truth and tell extreme truth. Now, if you thought that there's going to be any carryover from any of these conditions, the way to do it is just kind of vary up the conditions. Likewise, if let's say I was going to do something where I was going to have people come in at different times of day, there's something I thought day might affect, the time of day might affect how people react, and I had 4 conditions. I randomized that the order like this to try to control for time of day effects. Again, could we do something like this with an applied setting? And again, if you had different groups that were going to come in, receive different training, what you might do is try, and let's say you have something like different training facilities or different training methodologies, you might stagger the order, stagger randomly stagger this after what kind of training. A randomized block F test, quality of 2 or more means. Again, if it's 2 means, chances are we're just going to do a t-test. Variables, 1 nominal independent variable, 1 nominal variable that defines the blocks, and then 1 continuous dependent variable, again, with either JASP or SPSS. Those are going to be the variables where you get the scale sign, and they can be either interval or ratio data, or if we're working with Likert type scales, again, Likert type scales essentially being ordinal, but we can still analyze them like they were interval data. That was the definition of scale. If you ever work with Likert scales in collecting data, one of the things that you typically do, you're putting something together as some kind of questionnaire, perhaps a Qualtrics, MTurk, SurveyMonkey. A lot of times when you set it up, it's going to have it set up as like it's categorical data. So in other words, people are going to, indicate 1 for strongly disagree and 5 for strongly agree, and the data is going to come out appearing to be nominal data. And then what you have to do when you move it into SPSS or JASP is you have to reset the data so it recognizes that as being scale data, and sometimes you actually have to get rid of the labels. So block F test assumptions, and this is going to be anytime we're working with, could say ANOVA, but we could say anything that constitutes parametric statistics or ordinary least square statistics, OLS statistics. Again, OLS statistics are the statistics we take each observation, subtract a mean, and square it, which is going to include everything from ANOVA to t-test to regression, factor analysis, any of the multivariate, a lot of multivariate techniques. But the idea is, one of the assumptions is going to be that everything is going to be somewhat normally distributed. Homogeneity of variances, those variances are going to be roughly equal, not perfectly equal. And the idea here is that, especially if it's something where you're going to do some kind of treatment, the variances need to be about the same up front. So let me use the training example. I've got 3 different types of, or let's say I'm going to introduce 2 different types of Excel training in a workplace setting, and then some people are not going to get the training. And I'm going to evaluate people's ability on the training, or on the training, and compare that to people that don't get trained. Well, one of the things I might want to do is do a pretest, and what should happen with that pretest is if I randomly assign people either to training 1, training 2, or training no training, then the variances among those 3 groups should be roughly equal. And then afterwards, group 2 and 3 get Excel training, group 1 doesn't get any training. Afterwards, those variances either could be equal with big mean differences, or those variances could be unequal, with the idea that any variance difference at that point, if you start partitioning and identifying where the variation is coming from, it doesn't appear to be random. Okay, this should start to seem kind of old hat and redundant right now. Alternative hypothesis. No difference there, nothing to see, folks, keep moving. No treatment effect, all population means are equal even after treatments. Alternative hypothesis, not all are equal, and again, we don't know whether it's, all the groups or just one group. At least one population mean is different. Treatment effect, and the idea here is that the alternative, or the null hypothesis is wrong, because it's one group that's going to be different. Yeah, again, using that same kind of example. Well, no treatment effect, our distributions are going to look the same. If you look closely, there's a light blue line, darker blue line, and a purple line. And in this case, those distributions are pretty much the same, same shape, same everything. Now, again, would you really expect, if you plotted your data out and it didn't have any effect, would you really expect to see all the distributions just kind of pile up on each other? Probably not. There'd be some little bit of difference over the spring, but I think this makes it easier to see the idea that they're fairly the same and consistent. Now, that last example, the idea that how the means are equal. In this case, again, the illustration showing that we have one mean that seems to be a whole lot different than the others. So a treatment effect. Again, we could have a situation where all 3 of these are different, where, let's say, this is before, whatever we're doing, and after we've done our treatment of some kind, we have the distributions spread out quite a bit along the horizontal axis. So, explain this a little bit here. The F ratio for randomized blocks, total variation, total movement of numbers equals the error plus differences that occur because you block things out or you've staggered orders of presentation, plus the movement of numbers that's due to whatever the independent variable is. Now, basic script for the F ratio. How much of that variation or mean square treatment or mean square independent variable or movement within those numbers appears to be due to the independent variable, the variable of interest, and how much that MSE just means mean square error randomness. And then the calculations, the conceptual calculations. We're going to take the sum of squares total, we're going to divide it by the 1 minus the number of groups, or the number of groups minus 1. Sum of the squares it's within, and that's where we're going to compare each one of those observations to whatever the overall mean is for that whole data set. And easiest way to calculate the degrees of freedom is either, again, the total number minus the number of groups, or subtract 1 from each group and sum what's left over. And this should look a little bit redundant here. Test a statistic. The ratio, literally the ratio of how much variation is due to the treatment or the independent variable divided by the ratio of randomness. And again, this better equal more than 1. If it's close to 1, it means that the independent variable is equal to the randomness, so you don't really have anything. You're hoping for, even with small numbers, you're kind of hoping for that to be more than 2 or greater. Now, degrees of freedom, again, groups minus 1, and degrees of freedom total number of groups minus the number of blocks minus the number of groups, in this case, plus 1. Now, when are you going to have to calculate this when you're working with SPSS or CAS? Never. Software's going to do it. The idea with this is to, when the software is giving you the output, is to understand basically what's happening and how to interpret that. Now, again, use your imagination and see a fish or see a shark fin, whatever your preference is. Basically, what this is saying is it's identifying at what point in this distribution. So anything above this point right here becomes statistically significant because it's very low probability if it's up in this area, and that's what that line is telling you. Very low probability that this is going to be random fluctuation. That's literally what this means over here. This big area, this is how much area would assume that's going to be random fluctuation, usually 95 to 90% depending on what it is, or depending on whether type 1 or type 2 is. Now, this idea of one tail, with some tests we can have 2 tails. That is, if with something we're doing a t-test, where something can have a negative and a positive value, we can divide it over both sides of the normal distribution. F ratios are only going to be positive. Or another way of doing this is if you calculated, let's see, if you did an independent sample t-test 2 groups, that t-statistic, if you square it, and let's say instead of doing a t-test, you would have done a 2 by 1 ANOVA, or 1 by 2 ANOVA, which would make sense, but that F ratio would be the square of the t-statistic. And what happens when you square numbers, if you have a negative number, the negative sign is. Example using car tires. I think everybody can relate to car tires, right? Some of us don't work on our cars anymore, but we keep track of the tires. You know, after about age 20-something, when I started buying my own tires, I became really mindful of that, and really mindful of not driving in ways that wore the tires so, which you can't say I did in high school. When I wasn't paying for the tires, and, you know, lighting them up once in a while was kind of fun. Well, in this case, you wish to determine which of 4 brands of tires has the longest tread life. This is something that Consumer Reports would do this kind of research. So you have 4 brands here. And what you're going to do is you've got 5 cars you're going to use, but does it make a difference in terms of where you put the tire? Right? So my experience is the tire, let's say the back tires wear out quickest. I think it's probably the right front tire that kind of starts to wear on the outside edge because we tend to make more right-hand turns and left-hand turns. And not only that, we tend to make, and if you've ever tried to turn left on Farmerville Highway in the middle of the day, you can confirm this. If you ever try to make a left-hand turn, you're going to be sitting there for a long time. But if you make it, chances are you finally made it because there's no traffic and you're turning out very slowly versus, people a little bit more risky, a little bit quicker when they're making a right-hand turn because it usually doesn't mean there's the likelihood of hitting it. So that's about tires. Anyway, so we've got tire location and we've got tires. And we're going to try to determine which tire seems to last the longest. So randomly assign one brand A, B, C, and D to a tire location with each one of the 5 cars. And if you're looking at what's happening here, each car has a different tire on it. Right? So you've kind of controlled for some differences here. And this could actually work pretty good if you were running an experiment where you only had 20 tires to work with. But here's what happens if you were to go through all these numbers. Again, looking by the different blocks, then doing an average for all the numbers here and subtracting that average for each one of these to calculate the randomness, the mean square error. End up with something like this, where again, this should be kind of second habit. The null hypothesis, there's no difference. The alternative hypothesis, well, they're not all equal, but we don't know which one is not equal. The test statistic here. So we end up with an F ratio with that data set of 11.99 and some change. What it had to hit for us to say it's significant at 0.05 is it had to be at least 3.49. Well, if that's 11, 11 is probably going to be up here someplace. So we met that threshold. And again, at this point, we don't know which tire is better than which tire, or which position on the car, or which car for that matter. All we know is that there's a difference in the seat. So what we would do in that situation, and we'll work a little bit with this next week. Actually, we'll talk about this with an example I posted. We would have to do next is we would have to take a look at differences by car, differences by tire, and then the interaction of car by tire. Now, interaction, quick example of interaction. We'll talk about this later with an example that I posted. Three different types of movies. Train to Busan, The Conjuring, and I'm trying to think of the Paranormal. Are they different in terms of which one is more scary? I think a lot of people would say yeah. And the other question we could ask is, within those, are men and women scared differently by scary movies? And we could ask that question. We could look at the interaction. Are men and women differently scared by The Train to Busan, The Conjuring, and Paranormal? Seen all three of those?
I've seen Paranormal and Conjuring.
Okay. Train to Busan, that one you actually kind of have to look for. It's a movie that was made in South Korea it's like a zombie movie. They infect a train and start to infect the whole countryside. And somebody had actually done research to figure out which one was the most scary. I think most people would say that The Conjuring was the worst. Okay, so factorial design. More than one independent variable. Subject to assign randomly to treatment. Now, if you're me, you can kind of halfway do this if you're looking at something with some kind of training module where I could sort of take people from different work groups. Let's say I had 3 different kinds of training or 2 different kinds of training in a control group, and randomly assign people from different job types or different work units to one of those types of training, or one of the, we'll call that independent level training, 3 levels, no training, training unit, training type 1 and training type 2. So that I could do randomly. However, I would have one that could be a random effect and the other could be a fixed effect. Subjects are assumed. If we're assigning people randomly, assume that those groups are going to be homogeneous. And again, if you start assigning, more than 10 or 15 people, certainly once you get up to about 30 people, the groups are going to be fairly similar. And part of the reason that happens too is once you get about 30, outliers aren't going to influence things as well. Smaller numbers, one outlier can flip them. 2 or more factors are independent. Independent variables or variables of interest. Each has 2 or more treatment levels. Now, we said if it's just 2 groups that we're looking at, we would do a t-test. However, we take that t-test data, and let's say it's something we're looking at whether or not people were more scared by The Conjuring versus a paranormal activity. That's a t-test. If we say, okay, are men and women different with respect to which one of us is scary? Then it becomes an ANOVA because we have gender is one independent variable, 2 levels, and then we have movie, The Conjuring, and paranormal as being paranormal activities as being the other level, the independent variable with 2 levels. Now, every time we bring up gender anymore, people say, okay, it isn't just men and women, and we can look at gender as being, more than just a dichotomous variable. I understand the argument, but I think for purposes of here, we'll just go with that because of this.
So in my case, that's going beyond my area of expertise. That would be, that'd be a social psychologist question. I think the last social psychologist we had, that would be Jerry Tomacic, who kind of left us. Jerry knew everything. Jerry knows everything. He's, yeah, the most best cross-functional person we've had in part of who could do and teach just about everything. Well, anyway, analyzed at least by a two-way ANOVA. We could make it a three-way ANOVA. I've got an example next week where I'll show a five-way ANOVA. Once it goes past, my biased opinion on this is, once it goes past three independent variables, I'm looking for something else like multiple regression, because again, once we start adding variables on and creating more and more groups, the interpretation becomes a little bit more different. The advantages, time and effort. So basically what's happening is anytime you do something where you have a factorial ANOVA, where you have more than one independent variable, you're running multiple experiments. So how cool is that? You know, why just run one experiment with the same data and answer multiple questions? We use save time and effort. We use a completely randomized design for each variable if you choose. You have all kinds of different ways of being flexible with the groupings. Controls confounding variables by putting other variables in the model. So in other words, you could say, okay, we can take a look at how much, whether there's a difference on based on variable one, variable two, or is there something else in there that needs to be explained, because certain things only happen when you put certain variables together. Now, the unethical example I use in my undergraduate classes is, let's say we're looking at motor control, and we're going to do 2x2 ANOVA. So we're going to give you some kind of like a video game task where the idea is to get everything correct in the video game task, have good reaction time, and there's going to be two different independent variables. One is going to be beverage type, and the other is going to be medication type. The beverage type, you either get water or you get the equivalent of whatever pushes you up to 0.08 alcohol. Now, the medication type, you're either going to get a placebo or you're going to get Benadryl. I think everybody's familiar with Benadryl. It's one of those where, you know, it's allergy season and you have problems with allergies, but you look at the label and it says, you know, don't take this if you're operating machinery, heavy equipment, or driving, right? And the other thing about Benadryl is it's the active ingredient over-the-counter sleep aids. You've had Simonix or I think it's the other brand and stuff. Yeah, I'm familiar with the Benadryl. I think it's one of the handiest medications to have at home, if not for no other reason, because if you run into something where somebody starts to suffer from some kind of serious allergic reaction, it's usually a good medication to give people until you can get the EMTs there with the epinephrine. So in other words, if you had somebody who's allergic to peanuts or bee stings and something happened, you know, just give them a lot of Benadryl, you know, while you're waiting for the people to 911 to come. But the side effect for anybody that's tried it is the sleepiness. Now, if you look at that in terms of the conditions are water and no medication, so you're going to have, that's going to be one group. So 0, water, no medication. That's the impairment with respect to motor control is probably going to, not even going to happen. That's going to be the group that's going to have the best motor control response, the best reaction time response, things like that. You add alcohol will slow people. You add Benadryl will slow people. Now, if you mix Benadryl with alcohol, which the Benadryl label says not to do that, that's why I call this my unethical example, you're going to have what's called a synergistic effect, and it's going to compound both of those and make it really high. Now, it's going to have a real strong impact. That would be the interaction. So alcohol would have an effect, Benadryl would have an effect, put the two of them together and watch out. It's going to increase everything. So I'm told that's kind of a dangerous combination. Years ago when I was an undergraduate student living in the dorms, people at the end of the month, and again, I'm not going to recommend doing this actually, so don't do this, they would mix cocktails with club soda, vodka, and NyQuil. In other words, they're out of money, down to the last, whatever, quarter of the bottle of vodka. can't afford to go out anyplace, so let's put all this together. We're going to get super buzzed. We're going to hang out in the dorm and space out. Now, when I say don't do that, one of the biggest reasons for not doing that is the NyQuil contains acetaminophen. Acetaminophen is something you don't want to mix with alcohol because that can cause liver damage. And that's kind of what I saw happen too, that a number of people were rushed to the emergency room after doing that because of liver problems. Onset was within minutes. But anyway, I think that also illustrates, anyway, the alcohol to the Benadryl would be the interaction. So it just isn't just one, and an interaction could occur if, let's say, they were both equal, and we put it together, and we add that together, it's 2 times, whatever they were. With some interactions, you're going to be what are called synergistic, which is going to multiply the effect. So, point 3, explore interactions between per month variables. Kind of curious, do we have Lyft or Uber yet? We have no service.
Yes. Mainly runs in the crowd.
Yeah, my recommendation for anybody that's going out and getting intoxicated is to just drive. The chances of getting caught here are pretty high, but even worse than that, I've seen situations where people hit people, and the level of guilt they feel afterwards, this is pretty high. So 2A know that the equality of 2 or more population means when several independent variables are used, same results as separate one-way ANOVAs. So in other words, where we're doing more than one experiment, so we can test each one of those variables separately. So I can test the Benadryl and the alcohol, compare the alcohol to water with respect to reaction time, the Benadryl to placebo with respect to reaction time. But then I can also do this 3rd experiment where the interactions being tested. Now, realistically, if I was going to do something like this, what I might do is do some kind of training. It could involve software such as Excel. In the workplace setting, we have to bring people up to speed because they're going to have to report stuff. We're going to have to keep track of data using Excel. And so people get trained using either method 1, method 2, or not at all. And then I look by the different work units. So I've got one variable where it's going to be random assignment, and then I got the work unit variable. So people coming from engineering, accounting, production, or wherever. Those would be the ones where it becomes quasi-experimental. But I can still look at that interaction to see if there's, for example, there was an interaction of training type by work unit, then what it could tell me is that some people really, okay, I'm going to pull a Walsik here. Some people really excel at Excel after getting the Excel training. And it could tell me something about what training type works best for a specific group, or what group would benefit from the training. So when you're looking at all this stuff, this isn't just academic textbook stuff. This is stuff that you can actually use to apply settings. I've already stressed that about. Recognize anything here? So 2A ANOVA assumptions, normal distributions, whatever you're looking at, or reasonably normal, and homogeneity of variances, that is populations placed before treatments start off with the same or roughly equal variances. And independence of error. Now again, independence of error means that anything that's random doesn't correlate with anything else if it's truly random. We talked a little bit about regression. No, never mind. It's the psychometrics class. Okay. Anytime we measure anything, we're going to either have the value of what we're measuring, we're going to have the randomness. Now, with the example of measuring my height or my weight, that fluctuation was going to be the randomness. And if I took that measure and estimated how much of that was random, what should happen is if I'm doing that at different times of the day, I'm eating, I'm drinking, I'm doing things a little bit differently on different days and certainly different times of the day. So what should happen is anything that comes up as being random fluctuation should not correlate with anything else. It's just perfectly random. An example is, and we're going to go through this with some examples in here. So factor level A, factor level B, so very independent variable 1 or variable of interest 1 and variable of interest 2. And we've got different levels.
And what we're doing is we're crossing one variable with another variable and calculating means for each variable, each level of each variable, and each level of the other variable. Then what we're going to do is we're going to calculate means. We're going to say, okay, level 1 of factor B with level 2, or level 2 of factor A, and so on. So we'll go through the whole, if you want to call this a matrix. And so what we have here is, we're going to call these cell means because these are within cells. And those are going to be the interaction means of the test. What we'll have outside of these, we'll have something called the marginal means, and that's because they're not cells. Now again, we're just adding more groupings. We're crossing variables with other variables. And the idea is that we're going to do essentially what's going to be 3 different tests here. We're going to test whether the null hypothesis or the alternative hypothesis is correct for variable 1, for variable 2, or once we start crossing variables with other variables. Now, that in that example with Benadryl and the alcohol, if you would compare the placebo, the water group, the Benadryl and alcohol group, it really would come out as good. What also might happen is that the Benadryl group, no alcohol, the Benadryl water group and the alcohol, the Benadryl group might be close to each other, but they would be different than the no alcohol Benadryl. So same idea here, but instead of having just sources of variation due to error and due to one independent variable, we're going to partition this out. We're going to identify, the formula identifies how much the movement numbers is due to one independent variable, how much is due to the other, how much of that is due to one variable in the presence of other, or crossing them or mixing them together, and then how much of that is due to just randomness. I hope that makes that fairly simple. We talk about this next week. We're going to take this notion and we're going to break it down into a linear equation where basically what we're going to say is, we'll set this up where this equals this plus this plus this plus this. Okay? Real simple. Elementary school math, other than what we're adding together, a little bit past elementary school. Okay, the ANOVA table summary. We'll actually work on some ANOVA tables. We'll hand calculate all this out, but this is basically what you get out of just about any type of ANOVA software, where it's going to identify source of variation, variable A, variable B, mixing the two together, the randomness, and then the total. Again, this is put into sort of a computation. And if you look at what's happening here, we're also, we're identifying the sums of squares. So degrees of freedom, groups that are involved with A minus 1, number of groups B minus 1, take these two, multiply them together to get the degrees of freedom, the first set of degrees of freedom for the interaction. And then, take the sums of squares from each one of those, divide it by the degrees of freedom to get the mean square. Now, what's going to remain consistent across this is each one of these mean squares, because we're going to calculate how much of that is due to that variable versus how much of that is random. So we're going to take each one of those, we're going to divide it by that mean square error. In other words, for each one of these variables, what proportion coming from that variable and what proportion is just random fluctuation within the data set, with the idea that we hope that hits more than a higher value, more than 1. Otherwise, it's not going to be significant. So the interaction. Here's when effects of one factor vary over levels of other factors. So varies, does alcohol vary depending on whether or not Benadryl is used in conjunction with it? If I was looking in a workplace setting and I've got Excel training program 0, we're in the control group, training program 1, training program 2, do people who are engineers perform better on some kind of task or test of Excel expertise? Okay, I'm doing a Walsh again. Excel expertise going for the alliteration. Do they differ than, let's say, engineers or line workers? That'd be an example of line flow interaction. Can be detected in the data table, patterns of cell beans and row beans, We'll also talk about this in columns. The other thing we'll talk about is the graphing of data. And if you've ever produced a mean graph using ANOVA, when those lines cross, it pretty much tells you there's an interaction. Well, we'll get to that in a minute. So, and by in a minute, I didn't mean this particular example here, but with the problem that I've listed, the example problem listed this week, posted this week. So here we have effects of male, or effects of gender, male or female, and dietary groups. You know, whether eating normal diets, this is vegetarian, lacto-ovo, vegetarian, or strict vegan. Now, if you've looked at this stuff before, I'll give you an example of somebody who has been kind of impacted with this. If you remember who, I shouldn't say remember who, former President Bill Clinton. Bill Clinton left the White House, and within a year or so, he had gotten I think it was a quadruple bypass surgery because he'd had a lot of clogging of the arteries in the heart. And his response to that was, after he got the operation, was he became a strict vegan. So if he looks a little bit emaciated compared to how he did as president, a real strict diet. And of course, I think that's a good quality for anybody that's going to be a president, is to have that kind of discipline where you can do stuff like that. Well, you know, at this point, I'm not ready to try that and have any of the health problems that he had. So hopefully it stays that way. But one of the things that they've noticed is that cholesterol and systolic blood pressure. Let me explain systolic blood pressure. If you don't already know this, there's two blood pressure readings you get. I mean, normal is supposed to be 120 over 80. And the 120 is when the heart is contracting, and the 80 is when the heart is not contracting. So that's literally how much pressure in pounds is that blood putting on your vein walls. Well, if you're going to try to do something about heart disease, lower blood pressure is usually better. And in this example, the systolic blood pressure and diet, here you would have an interaction. So male blood pressure is higher under the normal diet and lowest with the strict vegan. Female blood pressure is highest with the strict vegan and lowest under the normal diet. Now, this is just arranged for illustration purposes. Chances are what you would find is something more like this, where there would be an interaction where people who are on a strict vegan diet would probably have the lowest systolic blood pressure, climb a little bit with the people that, the term here is, I think it's lacto-ovo. So in other words, people that are eating a vegetarian diet but are still eating eggs and consuming milk, and here's people that eating a normal diet. So they're going to have the highest systolic blood pressure. That's pretty good. So what Bill Clinton and what others that have had open heart surgery often try to do is they'll go for this one, if not this one, because what should happen is with the lower blood pressure, even if there's a cholesterol problem, should be less chance or more probability of that cholesterol plaquing in the arteries of any kind of significant way. So what would happen with this one is that cholesterol should go fairly low, unless you're from one of those families where your body just seems to produce that kind of cholesterol regardless of what you, which is like 3 or 5% of the time. Okay, so the effects of diet strict vegetarians, lacto-ovo vegetarians. So in other words, I'm getting all my nutrition from plants, getting most of my nutrition from plants, supplementing with eggs and dairy, or I'm eating a normal diet. I'm not even sure what constitutes a normal diet anymore. I see so many different ways people eat. But we'll just assume that that's where it involves the normal food groups, and you can starchy vegetables. Now, question. Test for the interaction main effects at 0.05. So in other words, the two things we want to look at here, we want to look at whether or not diet influences anything, whether there's differences in gender. And what I would say is, yeah, there are differences between men and women with respect to systolic and diastolic blood pressure. Typically, before age 40 or 50, women are going to be lower in both of those blood pressures compared to men. And part of that explanation, well, there's lots of explanations for that. Some of it is that men tend to lead unhealthier lives. The other part of that is men have more unbinded epinephrine and have more of a stress reaction than women have, or at least more of a physiological stress reaction. It's not saying that, when you're experiencing stress, you're not always having a strong, doesn't always mean you're having a strong physiological reaction. You can feel stressed out without having who you are and what your genetic history is like. Okay, so we've got those two groups, and then we want to know whether or not one of these diets works better or worse for men or women. Now, in this example, we have an interaction. We'd say the strict vegetarian diet led to the highest blood pressure for women. The normal diet led to the lowest blood pressure, and the opposite for men, if that was correct. Now, this is presenting a different outcome for that here. Again, that both genders are going to respond just about the same. If you see there's a difference between the lines here, men and women, a little bit of difference there, but this difference, depending on how big the sample is and what these numbers represent, this difference could just be random fluctuation. So we have different lines there, but they're still within the same confidence level. So linear contrast, this is something we'll talk about with post-hoc testing. So we're testing different combinations to see if there's differences. Now, there's an option in both JASP and SPSS that does this. So it's contrasting these to see whether or not there's differences based on standardized means, to see if you have either main effects or the species interaction effects. Contrast using least square difference test. Again, this is the most basic of the post hoc tests. The idea that it's going to essentially go through that t-test process where it's going to say, okay, here's the differences that are occurring among these means. And if the difference goes past this point, the math indicates that something other than random, or the probability of something random happening there is very, very low. And the Chaffee's test, this is the one I use the most in applied settings because it tends to be the most conservative, the strictest. And again, it's this idea that the t-statistic, but more complex way of calculating that error term. So in other words, what's happening here is this is the number that's being calculated to determine at what point does this value up here become statistically significant. Okay. So to go back over some of this, the key terms here, between sample variation or variation, completely randomized design. Again, this would be Walsick with his lie detection research. This randomly assigns people to different conditions and sometimes separates part of the conditions at looking at freshmen, sophomores, juniors, seniors, male and female. And again, the advantage of that, especially if you stagger the order of the presentation or control the time at which people assign the conditions, is that it gives you greater power to say something is or is not causing something. Experiment-wide error rate. And again, error for our purposes, we're talking about ANOVA, does not mean mistake. What it means is how much of that is just random. Factor, again, the terminology here is factor means independent variable. We're talking about ANOVA, and factorial means more than one independent variable. Levels. Any of our nominal independent variables are going to be said to exist in levels. Again, levels doesn't imply anything hierarchical. What it just means is that they're different groupings. Now, that's not to say you couldn't have something where it is hierarchical, but chances are, I should say, it doesn't necessarily have to be. Like the difference between male and female. One-way analysis of variance. So, anytime we have more than two groups, not to say we couldn't do it, one-way analysis of variance with two levels, but why not do a t-test since there's only going to be one comparison going on? But the idea is that we can take and look at anything we can define as being an independent variable that exists as groups or at a nominal level where it's groupings or categories. And we can have, conceivably have 100 groups if you want to do that. My bias on that, of course, by the time you push past certain numbers, don't use ANOVA because it's going to get too complicated. Total variation. How much movement is going on within a set of numbers? And what ANOVA does is it takes that total movement, total variation that's going on with the numbers, and breaks it down, and identifies what sources
with the idea that that F ratio is going to be calculated based on taking the variation that's coming from an independent variable, dividing it by the random variation, and hopefully that's greater than 1, so we can say that, okay, the independent variable is having some difference. However, once we get to that point, all we know is that there's a difference. We don't know what those differences are until we do post-op test treatment. Anytime we manipulate something, that's going to be a treatment, experimental treatment. Common experimental treatment for me would be doing something with training. With Toddy, it might be something like rearranging the work environment or changing work rules to increase perceptions that work environment is more good. Yeah, if you want some interesting examples, talk to Mitzi and ask her about some of the stuff that they do with reversal for workplaces where that's actually going to be a type of treatment. Within sample variation, this is going to be the same thing as error. So in other words, what's already going on within that group that isn't being driven by the independent variable. I will get a discussion post up after the video gets processed and loaded into YouTube. That's actually going a little bit quicker recently, I think. Probably looking at about hour lag time, so get this up probably 9:30, 10 o'clock. Now, the other thing I want to take a look at refresh my news screen here. It was a Word document that's labeled Factorial ANOVA Example 1. Open that up. Okay, so here's the idea. And this kind of research actually happens when movies are presented or screened, or let's say before they're released, they'll have a test audience. The test audience will watch the movie, react to it. They do this in a rather sophisticated way anymore, where people are watching movies and sitting down with a tablet or some kind of device, and then doing what are called pulse surveys, where they describe what they're feeling when prompted, or what they're experiencing when watching the movies. The other thing that they've done is they've done, like, to recognize what's happening here, heart rate and galvanic skin resistance and other physiological measures determine whether or not movies are exciting or scary or whatever. Because the idea is, people go to the movies not to sit there and be bored, right? So if you're trying to come up with a movie that's going to have a pretty good ticket sales, sometimes you'll do this before the movie gets released to the public. And the other thing that's kind of important about this, if you look at what happens with movies and what makes people decide to go see movies, a lot of times it's what happens during that first weekend that movie's out. I'm kind of that way. So in other words, I don't go to the movie when it's released. I wait and see what happens, if everybody else is interested in the movie or how people react to it. Well, the movie studios do this in advance. Something like that. In other words, if part of your genre is to produce something where it's scary, and I'm trying to think who the producer of The Conjuring likes to talk about making some of the most scary movies, being competitive with scary movies. Thinking of Paranormal Activity, which don't believe it's a stable set. And we'll do research where he'll test the movie, see how it's reacting. Now, in this example, let's say it's some kind of evaluation in terms of who has the scariest movie that we're looking at, and we have 60 female and 60 male participants, and we have them watch one of 3 movies: The Train to Busan, The Conjuring, and Don't Breathe. And rather than have people tell us they're scared, what we do is we take physiological measures. Now, the reason that kind of makes sense is if you look at what's happening here, men and women, okay? Who's more likely to admit the movie's scary? So, pardon?
Female.
Yeah, so women are more likely to admit it. Men are going to be sitting there, scared enough, scared out of their pants and say, no, this doesn't bother me, right? So if we do something where we take these kind of measures, and let's say we monitor people over the course of the movie,
and see what the average is with respect to galvanic skin resistance. Now, explain this one. This is, the more you sweat, the better conductor of electricity you are. This is like a lie detector test. So the lower the resistance, the more electricity being conducted, the more nervous, the more stressed out, the more scared you are. And then heart rate, you know, don't necessarily have to explain that one. The other one we could have done with this too, or the other one that could have been done to do this kind of measure would have been something where you're measuring people's respiration rates. In other words, you're scared, you're under stress, you breathe faster. We could also do something where we're measuring carbon dioxide. So the more scared you are, the more pooling of carbon dioxide you have, the more of that should show up in the breath. We could also have added blood pressure. But anyway, we've got these two measures, and you know, we'll put them together to create something we could call a fear factor. Okay, so once we have this, what questions can we answer with this? So, question number one: are men and women showing more physiological symptoms of fear? Number two, averaging across men and women, not even looking at gender. Are people on average more afraid of The Train to Busan, or show more fear, The Conjuring, or Don't Breathe? Then we take a look and see whether or not women were more affected, or how do women compare across those three movies to men across those three movies. Our interaction. Now, if you're looking at this, you might already have some hypotheses. Now, given that I haven't if I've walked into this with a theory saying that I think women are going to be more afraid, and I think The Conjuring is going to be the scariest movie, then I can set that up to where I say, okay, I'm going to use the least square difference test because it's lenient. I've already have a theory. In this case, though, if I was doing this, I'd say I'm not sure what to expect here. So when I analyze all this, if any of it comes up as being statistically significant, I'm going to go to my favorite test, the Shapey test, because it's going to be the most conservative estimate of what's really happening. Okay. The data set. If that would help. The data, if you have JASP, and let's say you put that data set is scary movie data, you put that on your desktop, JASP will find it right away. In other words, you don't have to have something that's configured for JASP. JASP will pull that up, and you'll be good to go. You'll be able to do the drop menus and pull up the functions. I'll give you a little video later in the week where I'll walk through some of the stuff on JASP. What's really cool about it is it doesn't take time to do the calculations like SPSS. What it does is as soon as you select something, it just magically appears on the right side. And again, perfect APA format. Let me see if SPS is disconnected. I'm going to listen to pull it up again. So, pull up the scary movie data. The black screen that was produced before is the SPSS copies on campus are connected to a site license, and it has to go through the server in Wiley Tower to identify that I legitimately have the program open. And when I didn't use this, it went to the course. Okay, so here's SPSS. Let me see if I can expand this. So anyway. Data view window, gender, numeric, I've got it coded as 1 and 2, but it is, you go over here, it's nominal data. That is, it's grouping data. That's the 3 balloons. Now, you're going to see these same labels in JASP. Now, the reason I'm not doing this in JASP right now is I can't download JASP onto the computer up here. Value labels. So this is coded so that 1 is female and 2 is male. So anything that's in the data row, once I click back on the data view, that first field, it's 1, it's female, it's 2, it's male. And then the other group, here's the movies. 1 equals Train to Busan, 2 equals The Conjuring, 3 equals Don't Breathe. Now, what we have going on here is we have a 2 by 3 ANOVA. We have 2 independent variables, gender and movie. Gender, 2 levels, male and female, obviously. Movie, 3 levels, Train to Busan, The Conjuring, and Don't Breathe. So if you're going to write this in terms of what kind of ANOVA, you're going to put 2x3. So 2 by 3, which means that we're going to test, again, whether there's difference in heart rate, pulse rate by male and female while watching, averaging across the 3 movies, whether there's a difference in terms of heart rate by Train to Busan, The Conjuring, and Don't Breathe, averaging across male and female. And then we're going to look at, again, whether men and women differ across these 3 movies. So in other words, we have 1 comparison for male and female. For the 3 movies, we'll have n times n minus 1 divided by 2. So we'll have 3 comparisons for that. And then we'll have 15 comparisons. So 6 gender by movie cells. So female, Train to Busan, male, Train to Busan, female, The Conjuring, male, The Conjuring, female, Don't Breathe, and male, Don't Breathe. And 6 groupings, n times n minus 1 divided by 2. So what we'll have is 15 comparisons there. So this gets kind of interesting in terms of what we can do with this. So do men and women differ? Do the movies differ? And within each one of those movies, do men and women differ with respect to any of these movies? Now again, variable number 2, nominal heart rate. Heart rate is scale. Scale is interval or ratio. In this case, we're working with true ratio data. And somebody, you could effectively, you could conceptually have a heart rate of 0, which means you would get. But you could say that, okay, somebody with a heart rate of 50 has a heart rate that's half the rate of somebody with a heart rate of 100. So it is definitely interval data. I'm sorry, ratio data. So going back to data. Now, if you're working in JASP, JASP isn't going to have that variable view window. What you're going to have to do to see those differences and do the labels is you have to click on the top of the column. This is what you'll see with JASP. So I've got gender, and remember, 1s are women, 2s are men, movie type. Train to Busan, The Conjuring, and Don't Breathe. The 1, 2, 3, those repeated across men and women, and then here's the heart rate. So our experimental question again, or questions are, do men and women differ with respect to heart rates watching these 3 movies? Do people watching these 3 movies differ regardless of whether they're men or women? And then do men and women differ with respect to the 3 movies? So what we'll do to try to calculate this, now if you're working in JASP, the drop-down menu on the side is going to ask you whether it's a factorial or no. It's going to be a whole lot simpler to find this. When we're working in SPSS, we'll do this, we're going to go for a general linear model. And again, this is based on the idea that we're going to partition the sums of squares. We're going to take all that variation, we're going to say it equals this plus this plus this plus this. In this case, the total variation is going to equal movie type, gender, movie by gender interaction, and then error. Now, the other thing we'll select here is univariate. What univariate means is I've only got 1 independent variable. Now, what we will be doing in here is we'll be doing some stuff with multivariate statistics, and I'm going to do that just to kind of illustrate what's happening or what you do with these statistics. I'm not going to try to raise a confusion factor. If you're having trouble with multivariate stats, I'm not going to count that against. That's a little bit past what we usually do. Now, univariate window opens up, average heart rate, and I'm going to use that as my dependent variable. And then gender, and let's see, movies and moving. I'm going to move that into fixed factors. Now, the reason I'm doing this is calling these fixed factors. I decided up front which ones I wanted to use. Now, with gender, again, if I'm going to keep gender as simple as male and female, I've exhausted all the categories. How would I call that a random factor? Well, if there was like a large array of different gender types, let's say there were 1,000 different gender types, and I went out and selected 2, that would make that a random factor. Likewise with the movies, chances are, if I use these fixed factors, well, chances are I wanted to see how these 3 compare
However, it could become a random factor. Let's say I had a list of 120 movies and I just randomly selected 3. Fixed factors here. Clicking on the model. The default here, if you don't click anything, is full factorial. Now, what that means is all independent variables and all combinations of independent variables. Now, down here where it says include intercepted model, we can click that off. I'm going to leave it on. It's not really hurting anything. What this is doing is it's going to take a regression type formula to do the actual calculations. What includes an intercept? That is where if you're going to say that this, you're going to try to calculate this as a regression model, that line is going to come into the axis someplace. We're just going to only line that's going to work. Contrast. Well, I could use this as a post hoc test. That was at 0, 1 matrix that we looked at in the presentation. But we'll just not mess with that this big class. Now, what this does is it takes the means and puts them on a graph. So if I want to say, okay, let's look at the means for men and women, averaging across all 3 movies and see what that looks like. We take those 2 data points and we connect them with a line. So add that horizontal axis and add. Now, difference. Let's graph the differences among these movies. Add that horizontal line and then add. And then what I'm going to do to test the interaction is I'm going to put movie type, horizontal axis, and let's say the test interaction on to see if there's graphic information that this suggests an interaction is there. So what I did here was I told it to plot the movies, but let's do 1 line for men, 1 line for women. So movie there, gender down there, click add, and move it down there. So we've got line for a plot for gender, we've got movie, and we've got movie by gender. Now, what should happen is if there's an interaction, those lines for men and women should cross. If they're parallel, it could mean that they're either the same or there's a main effect. Now, post hoc, what we'll get into this week is we're going to test the main effects. We won't get into the interaction. We'll get into the interaction next week. Now, a couple of things we've been talking about tonight. Least square difference test, Von-Brody test, Shapey's test. So here's what I've done to test whether there's a difference between men and women, and there's a difference between the 3 movie types. Taken a fairly lenient test and taken the Shapey's test. And let's see, with it. Yeah, I got it right. I thought there was 14 different tests. So that stayed consistent across the 2 versions. Now, the other thing is, we'll talk about this later. Equal variance is not assumed. There's 4 tests for that. Most of the time, we're going to assume this unless the program tells us that. Okay, so I'm going to test to see what the difference is. We'll continue on that. Save. If you're going to save stuff that was created in the calculations here, you would use this. Otherwise, most of the stuff will make it. With options, if I want to script this. In other words, do I want to see what the overall means and standard deviations were? Do I want to see what they are for gender, for movie, and for the interaction? And click on overall means. And then I could also ask for compare mean effects. Now, what's going to happen with male and females? If there's a difference there, it's going to tell you those post hoc tests don't make any difference because there's only the 2 groups. So it's only the one can know the difference from the other. We don't have to take a look like we would have. And try to figure out which one is more than. Okay, descriptive statistics and effect size and significance level. We'll leave that at 0.05. Click continue on that. And when everything looks like it's set up okay, then click OK. And that's not good. Oh, I see. It's not recognized. Oh, no, it's good. Try that again. I had problems with the site license. Other way. Okay, that's fine. Okay. In other words, I had to check with Wiley Tower to make sure I was complying with boot like copy of SPSS. Okay, if you look at what's happening here between subjects, factors, value labels, and kind of what I'm looking at here is, did it get the levels right? Did it get the counts moving through? So in this case,
60 men, 60 women, 40 watching each movie type. That looks good. Now, here's the descriptive statistic. And if you look at this, here's the means and here's the standard deviations. Well, if you look at the means, there's some differences in the numbers there. So the question is that difference random fluctuation or there's some real differences here? And even without looking at an F ratio or significance level, I'm kind of looking at this thinking, okay, there's 120 people in there. This is scaled from 0 to 100 and something. And consequently, I'm seeing some differences here where it's, 78 versus 100. So I'm going to assume that, well, I shouldn't assume anything, but I'm kind of thinking, yeah, this would be a good sign if I didn't already know what's going to happen because it's something significant. Now, the test of between subjects. This week we're talking about between subjects or between groups. Next week we'll talk about within subjects and within groups. Now, we have here corrected model. This is part of that regression formula. And if you wanted to interpret this, this is going to be like the overall amount of variation that's occurring. In other words, the F overall is 11.633. Well, that tells me that somewhere in there is a difference. However, I'm not going to look at it at this point because if I have an interaction, it kind of makes the rest of this sort of irrelevant. Intercept, again, we're not going to do anything with that. Now, over this column, partial eta squared. The significance tells us whether or not it's random or likely random or not random. What this tells us is how big that difference of those effects are. So we've got a fairly decent, what I would call a moderate effect size, moderate to large effect size happening with this data. So come down, and if you were hypothesizing a difference between men and women, follow this across. Here's the sums of squares, here's the degrees of freedom. This here is literally this divided by this to produce this. And then over here, the F ratios, again, this is going to take each one of these numbers here and divide it by that last number. In other words, this 11.63 is going to be this number divided by that bottom number. Same with all the rest of the numbers. Again, we're not going to work with that intercept. With this one here, gender 20 divided by 112.675, and there's the F ratio. Now, again, anytime something doesn't come up past 1, I'm just going to automatically assume it's not going to be significant. So if you're thinking there was a difference, if we were going to average across men and women across the 3 different movies, just say on average, or men and women different in terms of heart rate, if that's going to be some kind of indicator of fear, with this data, there's no difference between men and women. So kind of irrelevant. We go down to the movie. Among the 3 different types of movies, following that across, sums of squares, 3 different types of movies, 3 minus 1 equals 2 for the degrees of freedom. And this here, again, is this divided by this. Go over here, and this number is going to be this number divided by that number. So the number that corresponds to that row, 23.85.7 divided by 112.657 is going to give you that 21.177. And it's statistically significant. Well, going over here, anytime this goes below 0.05, it's going to be statistically significant. Now, if that's a 0 there, if you have 3 zeros, that means that before it actually hits a number, it's going to have to go up 1 more decimal places. The highest this could be right here would be 0.49. Because if it hits that 0.9, it's going to round that up to 5, and then it's going to round up to be a 1 in the next column. Well, 0.000 means, yeah, this really is significant, and probably very low probability what you have going on here is going to be random. And the partial eta squared, the moderate sized partial eta squared. Well, wait, before we interpret movie, we might want to interpret gender by movie to see if there's an interaction. So we come down to that row, and again, that same process. Gender by movie, and this degrees of freedom are just taking this degree of freedom for the gender, multiplying by the degrees of freedom for movie. 1 times 2 equals 2. Taking those degrees of freedom, or taking that, dividing it by that to produce that, and then taking that bottom number again and dividing this by that bottom number to produce the 7.816. And so we have an interaction. So the conclusion is, if we look at the movie level, those movies are differentially scary from one another, that one or more of those movies is scarier than the other two. But over and above that, there's differences based on that interaction in terms of what men and women find scary. Now, pairwise comparisons here. What's happening here is it's taking the men, or the mean for men, and subtracting from the mean from women, and giving what the mean difference is, average heart rate. And it's doing the same thing, opposite order there. Contrast, so if we're going to look at heart rate during movies, we've got between men and women, again, not significant. 0.674 is a whole lot higher than 0.05. So 67.5% probability that what we have is random fluctuation, and that 8 is squared at 0.002. I mean, most of the time, unless that hits 0.1, we're not going to deal with it. It doesn't mean anything. So incorrectly labeled moving, doing pairwise comparisons there. Well, we said that there was a difference between the two movies, so let's see where it's at. Now, what this is doing is taking the mean from the Conjuring and subtracting it from the mean heart rate for Train to Busan. And this is negative here. So what that means is this number is bigger than that number. Anytime we subtract a larger number from the smaller number, it gives us a negative number. And then we take Don't Breathe, the mean from Don't Breathe, and subtract from Train to Busan, and we get that number. Now, the asterisk there, significant at 0.05. So one conclusion here is that across men and women, The Conjuring was scarier than Train to Busan. Now what happens to the rest of these blocks is it does the same thing, it just changes the order in terms of which one of these is first. So The Conjuring, subtracting Train from Busan is the reverse of what was done up here. And again, 11.950, and significant at 0.05. So reinforces that. Now The Conjuring, subtracting Don't Breathe from The Conjuring, 14.450. So in other words, we have a positive number. What we did is we subtracted the smaller number from the bigger number. So The Conjuring comes up as being scarier than Don't Breathe. Okay. If you've seen those movies, this is about what you would anticipate. And if you want, Train to Busan is available on Netflix and Amazon Prime for free. So if you want to take a look at it, I wouldn't make it high priority, but if you like international films and indie type films, I think it's a really good film. But warning up front, it's in Korean with subtitles. So then Don't Breathe and The Conjuring, again, differences there. So what we have going on here, Train to Busan and Don't Breathe don't differ, but The Conjuring is the one that's different than the other two. So if we're going to say one of these is the most scary, it would be The Conjuring. Now, doing that same kind of analysis with a Chaffee's test. We did it with the least square difference test. Here's the Chaffee's test, and that same thing occurs. This actually, with the more stringent test, you demonstrated that either way that The Conjuring is the scariest of the three movies, and there's not really a difference between Train to Busan and Don't Breathe. We'll skip through this. Let's go to the graphics here. Now, here's the graphic with the mean heart rate of men and women averaging across the three movies. And if you look at what's happening here, women were lower than men, but we said that there was a difference between these two. And kind of to explain that is this is at 86, and women are 85.2. If you're going to find the zero, this is about 2 feet here. So if you're going to find the zero is going to be about 160 feet that way. Random fluctuation. Now, this is looking across the three movies. A little bit more to work with here. So this is about 83. That's about 82. I forget what it was, the data. But this during Conjuring, the heart rate goes about 95. So in other words, this kind of illustrates that pattern. Even though, let's say, okay, so the the zero line is going to be about
about 14, 15 feet down. So there's something going on. But again, you know, to really be able to see this, we have to start the origins of the graphics here. This is the one that's really telling you. So here's the line for men, here's the line for women, and the lines cross. And look at what happens here. So the interpretation here is that on average, The Conjuring was the scarier of the two movies, but it appears that men were the ones who were the most scared. So, and this, you know, come full circle with this. This is what kind of makes it legitimate to use those physiological measures, because we're going to go with self-report measures. Chances are, you know, men aren't going to, a lot of men aren't going to get to this. Right? But right? Well, this kind of paints the opposite picture. What we'll do next week is I'm going to introduce syntax that you have to put into SPSS and then for JAS. If I can get things set up so I can have a JAS computer in here, then we'll work with that and we'll test that interaction to see which, and what you're going to find with this is this could come up as significant, that's not going to come up as significant, this is going to really come up as significant. So again, you know, if you haven't seen all three of these movies, you might want to check them out and see if that's consistent with your opinion. The data I have here was actually shared with me from somebody else who took a lot of measures for the test audience, and this is as much data as you should. So, questions, comments, concerns? I'll put the discussion post up probably about an hour and a half. You all stay cool tonight. I'll get some more stuff up for you to take a look at during the week. Let me know how things are going with those problem sets, if things are making sense. And again, where we're going, this is like one of the toughest things that we're going to talk about in here. And the idea was let's hit this full force now, and then we'll kind of back off. We'll talk about the parts and the components with the idea that, you know, if we can do it in here, let's see if we can get everybody up to speed with multiple regression and some of the other stuff that you're likely using in the workplace. So on that note, oops, if I can get this to log off, I'll say goodnight and talk to you or at you all again next week.